This is now the part 2 of our Geotechnical Engineering lecture for the topic stress distribution in soil. Now previously, in our part 1 video, we are able to discuss the 4 formulas that we are going to use for this topic. The first one is the formula for stress caused by a point load. The second one, the formula for vertical stress caused by a line load. And the third and fourth, for the rectangularly loaded area, we have the first case wherein the increase in pressure is below the corner of a rectangular area, and the second case is the increase in pressure below the center of rectangular area. Now this time, in this video, we are going to discuss the 4th, 5th, 6th, and the 7th formula. So here we have the 4th formula, the vertical stress caused by a square and continuous footing using the pressure isobars based on Boussinesq equation for square and continuous footings. Okay, so how do we use this chart? So this is actually a chart. So we have here, it's actually a profile. So this is the plan. So this is the plan part. This is the top view, So plan, and then we have the plan. Then we have the cross-sectional area and the soil profile. So how do we use this chart? First, we need to plot the point where we are computing the vertical stress. We plot this having the horizontal axis as the x-axis and the vertical here as the z-axis. Okay, and we start our plot with the middle here as the 0. Okay, so the left side is this left portion is for the square footing, whereas the right portion here is for the continuous footing. So we need to plot the point wherein we have the formula for x. If we plot the x here, we have here the location of location of point divided by the measurement of the base, and for the z, for the depth, we have the also location of or depth. I should put here depth. Depth of point divided by the measurement of the base. Okay, and wherever the point falls in this chart, so for example, if it falls somewhere here, therefore the formula for delta P becomes 0.05 multiplied with Q. While if the point falls somewhere here, so we need to estimate what corresponding formula it gets. For example, in this point here, it is its range is within 0.05 Q and 0.02 Q. So we need to estimate what is the formula at that point. So this is 0.02, if this is 0.05, and this is the middle, this becomes so that is 0.02 plus 0.05 divided by 2, that becomes 0.035. So what is in between 0.035 and 0.02? So if this is 0.02 and if this is 0.05, what is in between them? So that becomes 0.02 plus 0.035 divided by 2. Therefore, we can estimate that this curve here to where our point here is equal to 0.0275 Q. So again, how do we get 0.0275 Q? That is 0.02 Q plus 0.035 Q, which we approximated here at this point here, that is divided by 2. Okay, so that's how we got the point. And the formula that we get becomes the formula for delta P. Okay, so that's for number 4 formula. Same is true with the continuous footing, but since it is continuous, we cannot get the value of L, but we can get the value of B. And this B here is the width, which we will use for these formulas X and Z. Right? Let's go to number 5. Okay, so the number 5 is the fastest way to get the delta P because it is approximate only. All we need to do is delta P is equal to the point load here, Q as the point load, divided by the measurement of the base plus the depth Z, multiplied with the length plus the depth Z. So that is the formula for approximate method. Next, we go to number 6, the vertical stress below the center of a uniformly loaded circular area. So for delta P, we have here the small q, which is the load per unit area. The unit there will be kilonewton per meter. And then that is multiplied with 1 minus 1 over r radius, the radius of the circle, divided by the z or the depth squared, plus 1, and then all of this raised to the power of 3 halves. Or we can use the second formula, delta P is equal to Q I sub 5. Now, where do we get I sub 5? I sub 5 can be taken from this chart here. Variation for I sub 5 with Z over R to be used. Okay, so the depth divided by the radius. So the value of depth over radius is located at the left part. So we can have here the location. So these are the values for Z over R. Then we wherever we get the value for Z over R, so we get the value for I sub 5. If ever there is no exact value for Z over R here, all we need to do is to interpolate using the interpolation technique that we used previously in the previous video. Okay. Next, number 7, we have the influence chart for vertical pressure. So this influence chart is the one presented by Mr. Newmark. And Mr. Newmark, 1942, presented an influence chart based on Boussinesq theory that can be used to determine the vertical pressure at any point, okay, so at any point below a uniformly loaded flexible area of any shape. So we can use Newmark's chart for any shape. The influence value of the chart is 1 over n, where n is equal to the number of elements. The figure below shows 200 elements, thus the influence value is, so given I is equal to 0.005. So this is the formula for influence chart, using influence chart by Newmark. So we have delta P is equal to IQN, where I is the influence value, Q is the pressure on the loaded area, and then we have N as the number of elements of the chart enclosed by the plan of the loaded area. So here is the Newmark's influence chart for vertical pressure based on Boussinesq theory. And then given I, or the influence value of 0.005. Here is the procedure. So the procedure for obtaining the value of N to be used for the equation. So remember, this is the formula. Given I, then this Q here will be given. So all we need to do is to find the value of N, or the number of elements. So we need N, and we use this chart. How do we use this chart? First, determine the depth, or Z, below the loaded area where the stress increase is desired. Number 2, plot the plan of the loaded area with a scale of Z equal to the unit length AB of the chart. So the reason why we need the depth Z is because the scale given in this chart here is based on the depth Z. So we need the value of Z. So if depth is 4 meters, then A to B is 4 meters, which we will use to plot or to draw the figure in this chart. Number 3, place the plan on the influence chart in a manner such that the point below which the stress is required is located at the center of the chart. So the center of the chart is where you will put the desired computation, or the point where we are getting the vertical stress increase. Number 4, count the number of elements N of the chart enclosed by the plan of the loaded area. If certain segments are not fully covered, you can estimate what fraction is covered. Okay. So we can show that later on in our sample problem. So these are the 4, 5, 6, 7 formulas to be used for computing the vertical stress increase. So let's continue solving the sample problem. So we are done with number 1, we're done with number 2, we're done with number 3, A to B, A to D. So we're done here already. So what we need to solve today is the E, F, G, H part. Okay, let's continue in solving this sample problem number 3. A rectangular concrete slab 3 meters by 4.5 meters shown below rests on the surface of a soil mass. The load on the slab is 1620 kilonewton. Letter E, determine the vertical stress increase at points A and B using the approximate method for rectangular loads. So we're going to use approximate method for letter E. Letter F, determine the vertical stress increase at points B and C using pressure isobars based on Boussinesq equation for continuous footings. Then letter G, determine the vertical stress increase at point A using Newmark's influence chart. Then letter H, determine the vertical stress increase at point B using Newmark's influence chart. Okay, so let's start with letter E. Determine the vertical stress increase at points A and B using the approximate method for rectangular loads. Okay, so let's have letter E, approximate method. So the approximate method is number 5, and it's delta P Q over B plus J L plus Z. Again, what is B? B there is equal to 3 meters. Yeah, is that? Yeah, 3, and then we have there L is equal to 4.5 meters. Z is equal to 3 meters. So from the formula delta P, so delta P is equal to Q, it's too near, so Q over B plus J L plus Z. And then we have here, what's the Q again? Given Q, that's the value of Q is 1620 kilonewton. So this is the value of Q, 1620 kilonewton. So we have 1620 divided by 3 plus 3, then we have 4.5 plus 3. Delta P is now equal to 36 kilopascal. So we have 36 kilopascal for letter E. Right? So let's go back to the question. Letter F, determine the vertical stress increase at points B and C. So the points here from the figure, we're looking for points B and point C. Point C is located somewhere here. So this is point C. We need to find the vertical stress increase using the pressure isobars based on Boussinesq equation. And for the Boussinesq equation, so this one here. Right? So let's solve for Boussinesq. For letter F, okay. Maybe let's use this. Right, so we have here the point C located here, and that is 2.7. So remember the Boussinesq equation, the chart, the pressure isobars here, we have here the point of origin at the middle of the footing, and we are to divide it at the base. So if we go back here, the base is 3 meters and our point of origin is at point A. So let's put here 0. Here. And to compute for the location, for the plot, so at point B, we have here x is equal to location of B divided by B, or the base. Okay, and then we have the Z equals depth. I think I should put here point B of point B, depth of point B over B. So we have here the location of B is 1.5, and the depth of B is 3 meters. So we put here location 1.5, and then the base is 3. Therefore, 1.5 divided by 3 is 0.5 of B. Okay? So 0.5 B, and then we have Z, look, depth of B is 3 over 3, so we have 1 B. Okay, so let's locate that point. So remember, we have here X is 0.5B, and then Z is 1B. And which one are we going to use here? Are we going to use the square footing, or are we going to use the continuous footing? So since it is a rectangle, our problem here is a rectangle. We are to use the right one, the rightmost, the right side, which is the continuous footing, having this as the base and L as the length. So since we have X as 0.5 and then Z as 1B, so we have here as the 0.0. So this is our 0.0. Our X now here is from this point up to 0.5. So this is our X here equals 0.5. Okay, so I hope it is clear. Yeah, so this is 0.5B. So 0.5B. The depth here is from this point here, the depth is 1B. So this is the depth 1B. So this is Z is equal to 1B. Therefore, our point B now is located here. And what is this formula? The formula here is 0.4 Q. Okay? So if this is 0.02 Q, this is 0.05 Q, 0.1 Q, 0.2 Q, this is 0.3 Q. Therefore, this curve here is for 0.4 Q. Okay? So it is 0.4 Q. So we found at point B, delta P is equal to 0.4 Q, 0.4 times 120, that is equal to 48 kilopascal. Next, let's find the point C. So this is point C. So at point C, what is X and what is Z? The location of point C is that is 2.7 meters. So 2.7 divided by B, our B is 3. That is equal to, what is 2.7 divided by 3? That is 0.9 B. Then for the depth Z, so this is point C. Z here is equal to 4.5 meters. 4.5 divided by 3, that is the base, that is 1.5 B. Okay. Then let's plot that in the pressure isobars using the green color here. So for the x-axis, again, I forgot to put here, this is our z-axis and this is our x-axis. Right? So x is 0.9b. If this is 1b, therefore our 0.9 is somewhere here. Somewhere here. Right? Therefore, my so this is x is equal to, so xc. Let's put here xb, zb, then this is xc. xc is 2.7, no, it's 0.9 B. Next, the depth is 1.5 B. So this is 1B, this is 2B, therefore 1.5 is in between them. So this is our Z. ZC is equal to 1.5 B. So 1.5 B. Therefore, our location now for point C is somewhere here. Okay, so there you go. And it does not hit any of the curves. So we need to find here what is this, what formula here. So we can always approximate. So the point C is located between point 3Q and point 2Q. So what we do here is, so at point C, so what we do here is we have point 2Q plus point 3Q, because I approximate it as in between them, so I just divide it into 2. That is equal to 0.25Q. Or if you're not satisfied with that, you can use somewhere much nearer to 0.2. I think it's much nearer to 0.2. So I can just approximate it and say that, okay, I believe it's 0.24. I can do that because it's approximation. So I think it's nearer to 0.2. So I say it's 0.24 cube, approximately. Oh, so 0.25 cube, but I will approximate it to 0.24 cube. Therefore, delta P is equal to 0.24 cube equals 0.24 times 120. So delta P now is equal to 0.24 times 120. So we have there 28.8 kilopascal. Okay, so that's how we use the pressure isobars of Boussinesq equation. So this is letter F. Okay, screenshot first. Alright, let's go back to the problem again. We're done with F. Let's go to letter G. Determine the vertical stress increase at point A using Newmark's influence chart. So we're looking for point A here. Right? Newmark's influence chart. So we're going to use this. And let's apply the procedure that we have read a while ago. And take note, we need to put the point where we are locating or we are computing the vertical stress increase. We are to put it at the middle. Therefore, point A should be at the middle. Okay. So let's go back here. So here is our pressure or the Newmark's influence chart. Okay, so this is the plan a while ago. Or maybe I could this is just to use as a reference. Okay, let's just use this as a reference. Remember, it says the what letter is this again? That is letter G. I believe it's G. Okay, so let's go back to the problem, to the instruction on how we get the value of n. So we need this chart to get the value of n. Number 1, determine the depth below the loaded area where the stress increase is desired. What's the depth of A again? The depth of A is 3 meters. So depth of A is 3 meters. So Z is equal to 3 meters. Therefore, here we have 3 meters. Z is equal to 3 meters here. This is our scale. Number 2, plot the plan of the loaded area with scale of Z equal to the unit length AB of the chart. Okay, so our scale here says that 3 meters is equal to this length here. So if I put here a line, this line here is 3 meters. So what's the line again? What's the base again? Here it's 3 meters. So what I will do here is I will put A in the middle. Put A here in the middle. And then I will get here the line. So so I cannot do that. Okay. Right. So this is point A. Let's use here. So I will use this as this scale of line here should be approximately equal to 3 meters. That's why you need your straight edge, your ruler, to do this, because you will be using it to draw the plan here. So I will first build the plan. Now if this is 3 meters, therefore 4.5 is something like this. So 3, this is 3 meters, this must be 4, then 4.5 meters. This is just approximate, but if you have your ruler with you, then okay. So I'm just going to use my ruler in this screen. I don't have any device for this application. So I approximate this. So I'm using a ruler, okay, which I'm trying to build. So of course it's easier if I use this application. So I'll just put it here. But what if we're doing it real time? Okay. So since I'm holding my ruler already, so what I will do here is I will take a 1.5 meter scaled here. So I have here 1.5 meter. Okay. Okay. Right? And then 4.5 divided by 2 is 2.25. So I'm going to use my ruler again here. So 2.25 should be equal to this point here. Equal to so then use your ruler or straight edge, draw a horizontal line and your vertical line. It's hard when I'm using straight edge on this screen. The pen is slipping. There we go. Then let's erase the excess. Okay. So that's the scaled. So this is the plan of the footing, and then we scaled it and we redraw it in this chart using this scale. Okay, so that's the idea on number 2. And then for number 3, place the plan on the influence chart in a manner such that the point below which the stress is required is located at the center of the chart. So we already do that. We put A at the center of the chart. Then number 4, count the number of elements N of the chart enclosed by the plan of the loaded area. If certain segments are not fully covered, you can estimate what fraction is covered. Okay, so let's go back. Here comes the counting for how many N. So how many number of elements N is present within this loaded area. Okay. So since this should be symmetrical. Anyway, let's just think this is perfectly plotted. So you can see what I already missed here is that it's not that exactly symmetrical. Okay, so let's just say it is symmetrical, right? So if we divide this into 4, we have 4 rectangles of should be similar in containing the number of elements. Then we can count on one quadrant here. We can count number of elements multiplied into 4. Okay, so I will get the number of elements in the top left portion. So this is a whole element here, whole element. As every whole element, I will count that as 1. So I have here 1, 2, 3, 4, 5. This is whole element. 6, 7, 8. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have 20 whole element. So I will now write here 20 whole element. Then I will now take the few fractions. Here, you can observe this is a fraction only of this entire element. So if you can see it, this is the entire element, but what is covered is only a fraction. I will say that this is a point, maybe 0.05. Okay, we can do that. So let's say it's point. I will write it outside 0.05. How about this? The element here, let's say that is 0.6. Then how about this one here compared to the entire element? So this is the entire element. This one here. So we'll say this is maybe 0.2, 0.3, okay, 0.3. And how about this element here? This is one whole element, but there's only this portion covered in the plan. So that's 0.75. How about in this element here, wherein this is the only thing covered? Say that is 0.7. How about here? There's a smaller one here. See, that is also 0.05. This one here. Right? And then we will put it in here. So 20 plus 0.05 plus 0.6 plus 0.3 plus 0.75 plus 0.7, then we have plus 0.05. Okay? Again, this is approximate. If you're doing this on your piece of paper, it will become more accurate because of your use of straight edge. There. Okay, so 20 plus 0.05 plus 0.6 plus 0.3 plus 0.75 plus 0.7 plus 0.05. That is 22.45 elements. Going back to the formula for number 7 formula is delta P IQN. So delta P is equal to IQN. Our I here is fixed, 0.005 multiplied with our Q, which is 120. The number of elements, 22.45. Delta P is now equal to 0.005 times 120 times 22.45. We forgot, it should be multiplied into 4. Remember, we had only one quadrant. So, this should be times 4. So, times 4. That is equal to, so 22.45 times 4 is equal to 89.8. So this is 89.8. So that is now equal to 53.88 kilopascal. Okay. So how do we know if we did not screw up? If our answer here is near to the previous answers, so according to what I have read, it should be near to the answer for 3-A. So 3-A, so that is B. So here, it should be near to this. So this one here, 51.88, we have 63, we have 37, so we have 53.88. So it says there, it should be near near the, or close to the answer using formula 3-A. Okay. So that's the last for letter G. For number 3, so this is the last. No, we still have H. Yeah, I see, there's still H. The last is H. Determine the vertical stress increase at point B using Newmark's influence chart. So we are to concentrate on point B. So this portion here. Again, we just have to repeat the same process. So this is H. Let's move here. And then this is the point B. right? So we need the value of n. And since this is b, we need to put b here in the middle. So this is point B. So again, using our straight edge, here in our scale, okay, so in our scale, Z is, again, that is 3 meters. So scale it here. So somewhere there. The B portion is somewhere. Okay. Oh. No, it's most farther away. There. Then 2.25. So 2.25. It should be somewhere here. And then 2.25 here. Alright. Okay, there you go. There. So this is our point B. Then since it's symmetrical here, we can get the measurement or the number of elements here, then multiply into 2. Okay, let's start counting. Let's start here. 1, 2, 3, 4, 5. So that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so there's nothing else, I think. So we have 28 whole element. So 28 plus the fractions. Fractions here, let's say this is 0.7. This is 0.9, 0.8, say 0.3, 0.1 or 0.2, say 0.2. Then this is say 0.1. Then this is 0.8, say 0.8. Then this is maybe this is 0.2. Yeah, maybe that's 0.2. Okay, so let's count again. 0.7, 0.9, let's add them up. This is 0.2, 0.3, 0.8 plus 0.1, 0.2. It's equal to 28 plus 0.7, 0.9, 0.2, 0.3, 0.8, 0.1, 0.2. 31.2. Then let's multiply it with 2. We have 62.4. And the formula is delta P equals IQN. Having I is 0.005, Q was 120, and then N is 62.4. We now have 0.005 times 120 times 62.4. We have 37.44 kilopascal. So let's see if this is near to the formula 3 dash. So it should be close or near. Answer for 3-A. So what problem we're in? We are looking for the vertical stress increase on point B using 3-A. Let's see the problem here. Okay, using point B. So this one here at part D. Okay, at D part here is 37.068. So we got a 37 here. It's very near. So it means we did not go wrong. Okay, so it is near. So that's for number 3. So we have 2 more problems, 4 and 5. Okay, last 2. Number 4, a square footing is loaded as shown. The center of the base of the footing is at coordinate 0, 0, 0. So this is a center of the, this is the center, I think. Okay. Oops. And then we have here. Okay, so we have here the center of the square footing located at coordinate 0, 0. Determine the increase in vertical stress at a point whose coordinate is 304 using pressure isobars based on Boussinesq equation for square footing. Okay, so based on pressure isobars so the coordinate 304 here, this is your X, Y, and Z. Z being the depth and X being the location from the center. So we're looking for point, so let's put here point P. Okay, so if this is point 0, 0, then this is x-axis 3 meters. This is 2, therefore it's located somewhere here. This is 3 meters. And then we have the 4-meter depth. So it's probably around here. Okay, so we have now our coordinate, and then let's plot it for the pressure isobars. So for the x-axis, we have there the location, which is 3. Again, we have here location of point divided by the measurement of the base, and that is equal to, the location is 3 divided by 2, so x is 1.5b. We have there z, that is depth of point, divided by the base, that is equal to, depth is 4 divided by 2, we have here 2b. So we plot it here in our pressure isobars. X is 1.5b, z is 2b. So we are concentrating at the left because we are using the square footing. So x is 1.5b, this is 1b, therefore our 1.5 is located, so this is 0. So this is 1.5 up to this point. So this is our x equals 1.5b. For the depth, we have there z is equal to 2b. So this is our z. Z is equal to 2b. So where is it now? It's located here. So this is our point P. And the question here is, how do we approximate getting this portion here? If this is point P, how do we get the approximate value? This is 0.02Q. This is the 0.02Q curve. This is the 0.05Q curve. Let's locate what is the formula for the midpoint of 0.05 and 0.02. What we will do here is 0.02 plus 0.05 divided by 2. Then we get that this middle curve here is 0.035. Now what's next? We get the 0.035 plus 0.05 divided by 2. So we have 0.0425 in this middle here. And since 0.0425, because 0.035 plus 0.05 divided by 2 is equal to 0.0425 Q. Since it's in the middle and it's already near this point, I will just approximate this as 0.044 or 0.043. Again, what I'm doing here is an approximation. So, okay, so I will approximate it as 0.044. So this curve here, I will note, is I approximate it as 0.044 Q. Okay, therefore, our delta P is now equal to P, that is 0.044 Q, 0.044 of 1, no. Where it's different problem. So what is Q here? (900 kilonewton). I should have computed it first. So 900 kilonewton divided by 2 squared. So 900 divided by 4 is equal to 225 kilopascal. So we have here Q as 225 kPa. So 0.044 times 225 is equal to 9.9 kilopascal. So that's for number 4. Okay, so screenshot first. So we have here our last problem, number 5. Determine the increase in vertical pressure at point 2 meters below point C. So this is our point C here. In the loaded area shown, the foundation applies a vertical stress of 250 kilopascal on the soil surface. So given Q is equal to 250 kPa. Okay, so all we need to do here is, so Z here is equal to 2 meters. So Z is equal to 2 meters. Our scale here is, our scale for A to B is 2 meters. So using our straight edge again, let's put C in the middle. So this is our middle part. And then let's have our straight edge. Okay. There you go. Alright, so I think we were able to, okay, let me double check. Then okay, so let's erase the excess. So this in this figure we okay, go. So in this figure we have 3 similar rectangular areas here. So this is 2 meters, 4 meters, 2 meters, 4 meters. So the number of elements on one of the square, we can just multiply it with 3. So n is equal to the number of elements for one square multiplied with 3. Okay, let's start the counting. So this is point C in the middle. Remember, we put in the middle the point we are considering. Let's start to count all the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so we have here 31 full element. Then let's get the fractions. So let's say this is 0.6, this is 0.9, this is this part here is 0.05 or 0.1. Okay, let's say it's 0.1. It's approximate. And then this is 0.6 also. This is 0.1. Then this is 0.9. This is 0.68. So it's approximating. Then put here 31 plus 0.6 plus 0.9 plus 0.1 plus 0.6 plus 0.1. So 6.9, 0.1, 0.6, 0.1, 0.9 plus 0.6 equals, so 31 plus 0.6 plus 0.9 plus 0.1 plus 0.6 plus 0.1 plus 0.9 plus 0.6. So that is equal to 34.8 times 2. No, it's times 3. I should say times 3. So this is 104.4 number of elements. Then, the formula for delta P is equal to I, Q, N. I is 0.005. Q is 250 times 104.4. So it's now equal to 130.5 kilopascal. Okay, so that's for number 5. So that's all for this part 2 of the video, and it's best if you practice solving them and find similar problems where you can apply them. The Newmark's influence chart is used if the shape is irregular. You can use the Newmark's influence chart. Okay, so that's all for